Okay, so this is just a talk through of the thermodynamics retest that you did last week. So the first question, it's about magnesium oxide, so we need to use this table below. It wants the definition of lattice dissociation. So lattice dissociation is where you have an ionic lattice, so it's the ionic lattice of magnesium oxide. It's going to be a solid, and what happens is the ions fly apart, or they're made to separate, and you're going to get magnesium ions and oxygen ions in the gaseous form. Okay, so you have to explain about what this is, and remember all of this has to be under standard conditions, but we also usually use 1 mole of something. So we're going to be using 1 mole of solid magnesium, it's magnesium oxide. It just happens it is 1 mole. So the magnesium oxide as a solid is going to be heated, and we're going to create 1 mole of magnesium ions and 1 mole of oxygen ions in their gaseous state. So we're going to take 1 mole of magnesium oxide of the compound that we are dissociating, and we're going to turn it into its ions. Okay, that's the equation for it, but you need to put it into words. My advice to you is you have some flashcards with the definition on one side and the with the keyword on one side and the definition on the other, so that you can test yourself on this. Look, this is a 3-mark question, and if you don't know the definition, then you're going to be losing 3 marks. It's all a matter of you processing this and learning it off by heart. Once you've learnt it off by heart, it'll go to the back of your memory, and you'll be able to recall it at any point, and it'll take no brain power whatsoever. Okay, so you won't be fussing over it because you will have learnt it off by heart. Okay, so a 3-mark question. The second one, in terms of the forces acting on particles, suggest one reason why the first electron affinity of oxygen is an exothermic process. So we've got oxygen. Oxygen is in, let me see, it's got 8 protons in its nucleus. It's got an inner shell of 2 electrons, and then it's got 6 more electrons. 1, 2, 3, 4, 5, 6 around the outside. So this is neutral. It's a neutral atom. So if you bring an electron towards that, because this whole species is neutral, you're not really going to get any repulsive forces at all. Now we've got 8 protons in the center here, so we're going to have some nuclear attraction for this electron, so it's going to want to drag it and draw it into that shell. So we get in attractive forces here, and this is energetically favourable. So once this electron has gone into that shell, it will release energy. It's an exothermic process. Once it's captured that electron, we've got O minus then, and if you're trying to bring another electron up towards this, we've got a negative species and a negative species. Let me do it here. We've got O minus and an electron. So once this has captured an electron, that's the first electron affinity. If we want to put a second electron in, that's the second electron affinity. This is a negative species, so we are going to get repulsion there. And because we're getting repulsion, we're going to have to put energy in to be able to get the second electron in, and that's an endothermic process. Okay, so that's an endothermic process. That's an exothermic process. And on our Born-Haber cycle, wherever we happen to be, an exothermic process is an arrow downwards, and an endothermic process is an arrow upwards. Okay, so this is going to be endothermic, so the arrow is going upwards, we're having to put energy in. This is an exothermic process, energy is being released, this is an arrow downwards. Okay, so we can have a look then at completing this Born-Haber cycle. So we do need to look at this. We need to see what's happening here, and actually we need to work it through our brains. So complete the Born-Haber cycle for mag oxide by drawing the missing energy levels. Look, levels is a few. You have to put the symbols and you have to put the arrows. So I'm going to look at this and I'm going to see what's happening. Okay, so I can see that this is our formation. We're forming the solid, so that's enthalpy of formation. I'm looking at this and there's no change here on the oxygens, but where the change is here on the magnesiums. So this is solid magnesium going to gaseous magnesium atoms, so this must be atomization. I can see here that the magnesium is losing an electron, so this must be the first ionization energy, and look, there's the electron that it's lost, so first ionization energy. I can see again that the magnesium has lost a second electron, so that's the second ionization energy. There's the second electron. Nothing's happened to that oxygen yet, so what I must be doing here is I must be taking that oxygen and I'm going to be atomizing it. Now what have I got here? I've got oxygen double bonded to another oxygen. What I do have is I have a half a mole of those. Okay, so I've got half a mole. I'm going to be splitting that bond and I'm going to be getting oxygen atoms. So I've got a half a mole of oxygen atoms. How many oxygen atoms have I got? I've got 2 oxygen atoms now. 2 times a half is 1. So actually that is 1 mole of oxygen atoms. So it's O gas. I've had to put energy in because I'm having to break that bond. Right, so if I draw that level, I've still got the 2 electrons and I've still got the magnesium ions as a gas. Okay, now the next thing I need to do, I need to, because I'm making magnesium oxide here, that's Mg2 plus O2 minus, so I need to make sure I ionize the oxygen. So what does it do? It's going to capture one of these electrons, and we've just been told back here, we've had to explain why this is an exothermic process. So we need to reflect that on here. So the exothermic process is going downwards, and okay, so this is an exothermic process we said before. So what I'm going to be doing is the oxygen is going to gain an electron, so it's going to be O minus as a gas. I've used one of those electrons, so there's the electron there. The magnesium hasn't changed, so magnesium 2 plus gas, plus that, plus that. Okay, now the next, now we've mentioned here, I explained here that when we put in the second electron, we've got repulsion forces and it's endothermic, so we should see that arrow going up. So at this point here, I'm going to be, I'm going to take that up here. Okay, so I'm going to add the second electron in, so magnesium 2 plus as a gas, plus, now that electron's been added into the oxygen, so it's O2 minus as a gas, okay, and that electron's disappeared because it's gone into that oxygen. So that is the second second electron affinity of oxygen. Okay, so from here we've got these in their gaseous form, and it is now they're going to form, they're going to come together and they're going to create this solid here. So we've got the gaseous ions coming together to create our solid. Okay, and that is our lattice, not dissociation and enthalpy, but it's our lattice formation. So lattice formation at that point. But do remember that actually if we go this way, this is just the opposite process, and that's the lattice dissociation enthalpy. Okay, so we just need to check what information we've been given as to whether that's lattice formation or lattice dissociation. What is it asking? Okay, it asks me to just draw the missing levels. Nothing on there. Okay, so complete the Born-Haber cycle by drawing in the missing levels. Standard enthalpy change values are given. Okay, fantastic. Right, so let's have a look at the next question then. Use your Born-Haber cycle. There we go. We've got it all drawn out. To calculate a value for the lattice enthalpy of dissociation. So it actually wants us to calculate this. Okay, so that's our lattice dissociation enthalpy. Right, so we need to put the values on these three here. So let's refer back to what we've got already, so what they've given us at this point. So this is the atomization of oxygen, and there's the atomization. So it is plus 248. So I'm going to put plus 248 on that. First electron affinity, that's this one here, is minus 142. Well, that's good because it's going down and it's a negative value, so perfect. This one is going up. This is the second electron affinity, and that's plus 844. Wow, look at that. Big change there. That means there's a lot of repulsion. We're having to use a lot of energy to put that second electron in, compared to this, which is we are getting 142 kilojoules of energy back out of this by adding the first electron in. Okay, so we've put all three in there. Now, this is really where we need to be looking. So if we're going to go from magnesium oxide to the lattice to the top here, which is our lattice dissociation enthalpy, what I'm going to write down here is that's the lattice dissociation enthalpy. That's what I want to find, and that equals. So now, from my cycle, I'm starting here. This is my starting point, and it doesn't matter where I start. The paths, we will get to the same path, but we'll just have to take into account the signs. So I'm going from here up to lattice, up to this, these gaseous ions. Okay, so that's one route round to the circle. The other route is to go from this way. I'm going to use a different colour, blue. I'm going to go this way, and I'm actually going to go this way round the cycle to get to the same finishing point. Okay, now this is the interesting bit. Lattice dissociation enthalpy to get to there is equal to, and I'm starting from here, so I'm going up this way. Now you can see I'm going against this arrow, so I want the arrows to point the same way. So if I flip that arrow so that it points the other way, I'm going to have to change the sign on here, and that's going to be plus. So this is plus 602. The next one is plus 150, plus 736, plus 1450. I'm going up again, plus 248. I'm going with the arrow, so with the arrow I'm going to keep the sign, so minus 142. I'm going with the arrow, plus 844. Okay, so what I need to do now is to add all of those together, which I'm just going to pause, and I'll do that calculation now. Okay, so I've put that information into my calculator, my very old calculator, and it's given me a value of 3888 plus 3888, so plus 3888. It's all in kilojoules, so kilojoules molten the -1. Now, is that correct? It's a lattice dissociation enthalpy, so I'm having to put energy in to break up the lattice, so to go from the solid to the gas. We know it's got to be positive. My answer is positive, so that's it. I'm going to leave that as the answer, plus 3888. Okay, so moving on then, we're going to look at the standard free energy change for the formation of magnesium oxide from magnesium and oxygen. Okay, so suggest one reason why a sample of magnesium appears to be stable in air at room temperature. So what this is saying is that if we mix or we react magnesium with oxygen, I'm going to have I'm going to balance this up. So 2 magnesium oxides. Actually, that Gibbs free energy is minus 570 kilojoules per mole. So what do we know about negative Gibbs free energy? If it's negative, it's not feasible. It's not going to react. So it says, suggest one reason why a sample of magnesium appears to be stable in air. Sorry, there's something I said there. Delta G is negative, so that means delta G. If delta G is negative, it means the reaction is feasible. So here we've got the delta G. It says the reaction is feasible, very feasible. But actually, magnesium won't form magnesium oxide very easily. This is what it's saying. Suggest one reason why a sample of magnesium appears to be stable in air at room temperature, despite this very high negative delta G. One thing that we learnt at GCSE, magnesium forms a protective layer around it. So here's we've got magnesium, and if we were to look at it, it has a protective layer of magnesium oxide around it. One of the reasons that magnesium doesn't, well, corrode. Okay, so this is magnesium, whereas iron will corrode. So iron doesn't have a protective layer of oxygen around it for iron oxide. So when we were talking about rusting back at GCSE, we used this idea of this magnesium oxide coat, making it more resistant to corrosion. Magnesium does that. Aluminium also does the same thing. So aluminium can have an oxide coat around it which protects it. So from our GCSE knowledge, we know that there'd be this magnesium coat around it, magnesium oxide coat. So one reason could be that it's got a protective layer of magnesium oxide, so the oxygen can't get in to corrode it any further. It'll just do surface corrosion, and that's it. So that's one possible reason. The second possible reason is actually at room temperature this reaction's very slow, so very slow reaction is another reason. And also the activation energy is quite high, and we know this because when you get magnesium you have to put it in a Bunsen burner to actually get it to work. So you're having to give it a whole heap of energy to surmount that activation energy barrier before it'll work. So the activation energy is quite high. Okay, so with this one, delta G as negative means it is feasible, but it's not a quick reaction. It has a protective layer of magnesium oxide around it, and the activation energy may be too high for it to do that at room temperature. We don't have enough energy at room temperature. Okay, so let's have a look at the next one then. So use the value of delta G given in E and the value of delta H from part C to calculate a value for the entropy change delta S. Give the units of delta S. So regardless of what you have calculated for delta H, use it, and if you use it correctly you will get full marks here. But ideally we want you to use the right delta H. So we've got delta G equals delta H minus T delta S. What does it want us to find? It wants us to find a value for the entropy change delta S. So it needs us to find this for 1 mole of magnesium oxide. So what do we know? Delta H we've just calculated. Hang on. Use the delta H of formation from part C. Okay, that's this one here, and that's delta H of formation, so that's down this way, and that's minus 602. So we're going to use delta H is minus 602. That's delta H of formation. Delta G, did we just work that out? Delta G, it's just given it as here, hasn't it? Minus, oops, let me just do that here. It's given it as here as minus 570. Okay. It's a bit naughty this, because it's making you turn the page. Minus 570 kilojoules, they're all kilojoules. And the temperature it's given us at 298, so T equals 298. So we've got everything that we need to be able to calculate delta S. This needs you to rearrange the equation. Okay, so if I were to rearrange this equation, it'd be delta G minus delta H equals minus T delta S. And then delta G minus delta H over T equals minus delta S. I probably want to get rid of that minus sign, so if I multiply both sides by minus 1, then minus 1 times minus, and that's a 1, would become plus 1, and minus 1 times all of that, I'm going to just put a minus in front of that, so that's going to be minus there. Okay, and then I can just substitute in, so I'm going to substitute in minus 570 minus 602, so that'd be plus 602. The temperature is 298, and I should get a value, so minus, that's going to be minus, and I'm going to put minus 570 in there, and minus 602 would be plus 602, and this is 298. Okay, so minus 570 plus 602, that's going to be a positive number, and then I've got a minus outside, so overall it's going to be minus, divide by 298, and it will give me the delta S. You can work that out. Okay, so that's the first one. In terms of the reactants and products and their physical states, account for the sign of the entropy change that you calculated in part F. Right, I'll go back and I'll calculate that and I'll work out what the sign is. Okay, so I've done that calculation and it's minus 0.107. It's in kilojoules, and our entropy here, because it's so small, we change it to joules, so this is 107 joules per mole to the minus 1, so it's minus. So in terms of the reactants and products and their physical states, why is that sign negative? So we're still looking at magnesium, which is a solid, reacting with oxygen, which is a gas, to give us magnesium oxide, which is a solid, and I'm going to balance that up. Okay, so in terms of the reactants and products, so we can see here the reactants are 2 moles of solid and a mole of gas going to 2 moles of solid. So this is somewhat disordered because we've got the gas here, but actually we're creating a very ordered system here. So in terms of entropy, the entropy is going to go down, so we've got more disorder on this side of the equation, on the left hand side, than we have on the right. So this is going to be a more ordered system, so hence we would expect the entropy to be negative because it's becoming less disordered, more ordered. Okay, you can talk about that there. Next one, let's have a look. So we're on question 2 then. This table contains some values of lattice dissociation enthalpies. Okay, so magnesium chloride, calcium chloride, magnesium oxide. We calculated it at 3888. So, you know, if we'd have looked earlier, there it is, 3888. Here it is again. Actually, we could have got that answer. So sometimes it's worth looking forwards in the paper. It says write an equation including state symbols. Look there, including state symbols for the reaction that has an enthalpy change equal to the lattice dissociation enthalpy of magnesium chloride. So basically it wants you to show that magnesium chloride will dissociate into its ions. So let's go with magnesium. We know it's group 2 plus. It's going to be oh, hang on, let me start again. Here's magnesium chloride, so we'll just write magnesium chloride in the solid state. It's going to go, lattice dissociation, it's going to go to magnesium ions in their gaseous state and chloride ions in their gaseous state. And we've got 2 chloride ions, so we need to put a 2 in front of that. Okay, so that's the lattice dissociation enthalpy. That's what it's asked, with state symbols. Okay, don't put state symbols, don't get the mark. Explain why the lattice dissociation enthalpy of magnesium chloride is greater than that of calcium chloride. Well, we've got chlorides in there, so it's the same size chloride ion, but let's look at the size of the magnesium ion. So we've got a magnesium 2 plus ion and a calcium 2 plus ion. So they've got the same charge. However, what period of the periodic table are they in? This is in period 3 and this is in period 4. What does that mean? Calcium has got one more shell of electrons than magnesium. So actually magnesium will be a small ion, whereas calcium will be a big ion. So in terms of charge density, so that's the charge per unit volume, the volume of magnesium 2 plus ions is much smaller than the volume of calcium 2 plus ions. So the charge that we've got on here, 2 plus, is going to be more concentrated than this on calcium, which will be bigger. So as a consequence, here's our chloride ion. Let's say it's that big. The attraction is going to be greater here because this is more dense positive charge than it is here. So this attraction is stronger there, and it's going to be less strong here. So it's less strong than the magnesium. Okay, so you can put that into words. Okay, so let's have a look at C. Explain why the lattice dissociation enthalpy of magnesium oxide is greater than of magnesium chloride. Right, look, we've got the same magnesium ion. It's the chloride ion and the oxide ion that's changing. So we know that a chloride ion is negative. It's actually quite big. Chlorine is in period 1, 2, 3. It's in period 3. Oxygen has got a 2 minus charge. It's actually in period 2. This is a bigger ion, it's got less charge. This is a small ion and it's got more charge. So if we're looking at charge density, this is a small highly charged ion, so it's small and highly charged. So in terms of charge density, this is going to have a whole heap of charge density, whereas this is not so small, so it's a larger ion and it's got less charge, it's -1. So if we've got our magnesium ion here in the centre, what's it going to be attracted to? This is only a 1 plus charge. The charge density, it's more spread out, so it's very unlikely to have strong ionic attraction. It will have ionic attraction, but it's not that strong. Whereas here we've got a small highly charged ion with a small highly charged ion. The attractions here are much greater, and if they're much greater, it takes more energy to break that ionic bond. So in that case, the lattice dissociation enthalpy for magnesium oxide is going to be greater than magnesium chloride. Again, you can write that in your own words. Okay, looking at D then. When magnesium chloride dissolves in water, the enthalpy of solution is -155. the enthalpy of hydration of the ions is this. Right, this is a Hess cycle. Okay, and it's knowing how to draw the Hess cycle. Magnesium chloride dissolves in water. So we've got magnesium chloride, so it's a solid. It dissolves in water. So if it dissolves in water, we're going to get magnesium ions, which are dissolved in water. That's what AQ is. And we're going to get chloride ions, which are dissolved in water, which is what this is. It's told us that enthalpy of enthalpy of solution is minus 155 kilojoules. The next part is to do the rest of the cycle. So this is down here. What are we going to do? We're going to make magnesium ions in their gaseous state and chloride ions in their gaseous state. So we can use that lattice dissociation enthalpy to break that solid into those ions. So that's lattice dissociation enthalpy. I'm sure we've got a value for that somewhere. And then here we are hydrating those ions. So this is the hydration, not solution. Solution is when you dissolve a solid in water. We are hydrating those magnesium ions. So that's hydration for magnesium and hydration for the chloride ions. And just look, we've got 2 chloride ions here. So whatever that is, it's 2 times. Whatever that value is 2 times. So I'm going to quickly flick over and see what we've got. So the lattice dissociation enthalpy for magnesium chloride is 2493. So 2493. It has given us the enthalpy of hydration for the chloride ions. Excellent. So that's 2 times minus 364. And this, it's asked us to calculate the enthalpy of hydration for the magnesium 2+ ions. Okay, so this is where we construct our Hess cycle. So we can go, if we go from here to here, it's the same as going around the cycle from here to here. Okay, so let's put that together. So minus 155 equals, this would be plus 2493, up this way, plus 2 times minus 364. So what is 364 minus times 2 equals, so that's minus 728. So minus 728, and we're going to add the enthalpy of hydration for the magnesium 2+ ions. Okay, so sorry, that should really be on a line, but I don't have the space. I do need to rearrange this equation, so I'm going to take this value to the other side. I'm going to take this value to the other side, and that would leave me with the delta H, the hydration for the magnesium ions, as the left hand side. So I'll do that now. Okay, so I've taken those over to the other side. So minus 155 minus 2493 plus 728 equals the hydration enthalpy for the magnesium ions. I've simplified that. I've done the calculation, and my calculator says it's minus 1920. So that equals minus 1920, and that is kilojoules per mole. Does that sound right? I'm taking gaseous ions, I'm hydrating them, they're highly charged, the water molecules will be attracted to them, it's an exothermic process, I should expect a negative enthalpy. And there we go, we've got a negative enthalpy. So that in effect looks quite right. So that would be my enthalpy of hydration of those magnesium ions. Yeah, I've just had a sneaky peek at the look at the answer, and the answer is minus 1920. Phew, I'm glad about that. Okay, so let's have a look at this then. Energy is released when magnesium ion is hydrated. Well, thank you, because we've just worked that out. Thank you very much. Yes, we know that. Because magnesium ions attract water molecules. I think I said that earlier. Explain why magnesium ions attract water molecules. You may use a labelled diagram. Oh, diagram. Excellent. So, let's draw water then. Okay, water. Okay, we know water is polar. We know water has a lone pair of electrons. We can work that out from shapes of molecules. So we know that this end is delta negatively charged. Also, oxygen is more electronegative, so it is going to attract more of the electron share than the hydrogens, and this end is delta positive. Okay, now we've got our magnesium ion, Mg2+, and what do we get? We get attraction between the delta negative end of the water molecule and the positive charge on that metal ion. So this is attractive forces. They're not intermolecular because this is an ion, so I'm just going to call them attractive forces and be a little bit more vague about that. So where do we score the marks? We score the marks on the fact that we've shown that this is polar, so that would get us the mark. If we didn't draw the diagram, we'd have to say that water is polar, oxygen is slightly negatively charged, whereas magnesium is positively charged, and so we get an attraction, and I've said that's an attractive force. I've pointed it out, and I've pointed out that that's positive. So water's polar, and that magnesium ion attracts the negative end of the water, and I've shown it, so that would be the 2 marks. So that diagram literally answers that question. Okay, let's move on to the next question, which is here. Suggest why a value for the enthalpy of solution of magnesium oxide is not found in any of the data books. Well, I guess this is, I looked at this and I thought, what does it mean? Well, what it means is magnesium oxide doesn't exist as magnesium oxide. Magnesium oxide reacts with water. And it forms magnesium hydroxide. So you don't actually get magnesium ions and oxide. It's this oxide ion. You don't get these oxide ions in water. What happens is this part would react with the water, and we make magnesium hydroxide. So magnesium oxide as a solid, if you add it to water, I'm going to have to put H2O here, you don't get hydrated oxide ions, you get hydroxide ions. Now that's a really sneaky question. Okay, oh, that's it. Yeah, you get so it's really, really sneaky. So this is one of those that now you've met it, you'll remember it. So what it is magnesium. So we say that magnesium oxide reacts with water to form the hydroxide, to form magnesium hydroxide. Okay, and that's it. That's the answer.